Hello everyone. These days, national IPv6 action policies encourage developing innovative IPv6 enhanced technologies. Meanwhile, new services such as the IoT and the mobile internet develop quickly. These trends drive the internal application and the networks of enterprise to evolve to the IPv6-only architecture. Such evolution is a long-term and gradual process. Today, we'll introduce the general IPv6 evolution path plan on the enterprise networks. The enterprise network architecture is a necessary part of the IPv6 evolution path plan. Based on the networks of large organizations and enterprises, the network architecture falls into three scenarios: data center, WAN, and the campus network. Typically, the enterprise internal basic application systems and the public services, like external port websites, are deployed in the data center. These involve key modules, such as external internet interconnection, internal WAN interconnection, and the internal network deployment of the data center. IPv6 reconstruction of the data center is typically driven by service upgrade. The enterprise private WANs are either built by enterprise itself or leased from a carrier. These WANs provide connection services for campus networks to access internal application of the data center. Generally, the self-built private WAN is a key channel for the enterprise internal communication. To lay a solid foundation for interconnection, IPv6 reconstruction must be performed. The leased WAN can be gradually upgraded with the IPv6 reconstruction of branch campus networks. Enterprise branches and subareas are widely distributed. The production and office campus networks vary in scale. Also, multiple branch campus networks mainly access the internal application systems of the data center. As such, the IPv6 reconstruction of the campus networks can be gradually performed alongside the IPv6 reconstruction of internal applications in the data center. The IPv6 evolution path plan of enterprise network should be considered based on enterprise's basic network architecture from the aspects of networks, services, and users. It should focus on ensuring the service continuity, the accumulation of IPv6 technical experience, and the long-term smooth evolution feasibility. It should also prioritize the requirements of national IPv6 action policies. Based on these factors, the IPv6 evolution path includes three phases. The first phase prioritizes the national policies requirements and lays the network foundation for continuous evolution. These are three main tasks involved in this phase. First, the task of the first phase: complete the restructuring of external public services. External public services are typically developed in the DMZ, in the enterprise data center. According to national policies, the reconstruction of the DMZ for external public services must be prioritized. This reconstruction involves the Internet Egress Zone, DMZ, and the corresponding external public service application systems. Deploy the dual stack solution is recommended to meet the internet access requirements of both IPv4 and IPv6 users. Second task, complete the IPv6 reconstruction of the enterprise WAN. The enterprise WAN connects the campus networks and the data center. It's the key channel for communication between internal users and applications. Prioritizing IPv6 reconstruction of the WAN is recommended to lay a foundation for large-scale reconstruction of the campus networks and the data center. It is also recommended that IPv6 be used for the enterprise's WAN reconstruction to implement IPv6 single stack on the underlay network. Also, it is advisable to deploy in the dual stack tunnels on the overlay network to meet the transport requirements of IPv4 and IPv6 services during the transition. Third task, construct an experimental end-to-end IPv6 environment to support continuous evolution in the future. Internal applications of enterprise data center need to be gradually developed and reconstructed. In the first phase, select a pilot campus network and create a test zone in the data center. Then perform IPv6 reconstruction for both the pilot campus network and the test zone to establish an IPv6 communication channel between them. This will provide an end-to-end test and verification environment for application system reconstruction, enabling smooth upgrade of internal applications. In addition, we can accumulate IPv6 technical experience based on the end-to-end network. In the second phase, fully upgrade the internal application systems of the enterprise and preferentially select IPv6 channels for mutual service access. There are three main tasks involved in this phase. First task, fully upgrade the data center network and deploy dual stack on it. This provides a network base for deployment and rollout of new service systems, or reconstructed ones. Once some internal services systems have been deployed and reconstructed, as well as have passed the end-to-end verification in the test zone, they can be deployed and brought online to provide IPv6 services for internal users. During IPv6 migration, internal IPv4 and IPv6 users coexist. As such, the internal application systems of the data center should be deployed in dual stack mode to allow concurrent access of both IPv4 and IPv6 users. Second task, promote IPv6 reconstruction of the enterprise office campus networks. As IPv6 reconstruction of internal applications in the data center deploys, enterprise can start IPv6 reconstruction of office campus networks. It is recommended that IPv6 reconstruction of the headquarters campus network be completed first to create a baseline for IPv6 campus network reconstruction. Experience gained during the construction of the headquarters campus network can be used in the construction of branch campus networks. We can also determine the 10 points for switching dual stack tunnels to single stack tunnels on the line to promote campus network reconstruction. Third task, complete dual stack reconstruction on production campus networks. With the development of smart manufacturing, IoT application system will be widely deployed on the enterprise's production campus networks. Because of huge numbers of terminals accessing the production campus networks, these networks must be quickly reconstructed to support IPv6. In this way, we can provide sufficient address space for so many terminals. A large number of old production systems and terminals still exist on the production campus networks and cannot be directly upgraded to IPv6 single stack. Therefore, the networks must retain IPv4 connections. In other aspects, new IoT systems and terminals support IPv6 single stack, and their communication is typically closed on the production campus networks. For these systems and terminals, IPv6 single stack is recommended. To meet the communication requirements of both old and new application systems, it is advisable to deploy dual stack on the production campus networks. In the third phase, the internal applications of data center are gradually switched to IPv6 for communication, and the IPv4 communication capability is reserved for internet access. In this phase, we focus on gradual IPv6 migration of internal applications in the data center. After migration, the data center network, internal application systems of the data center, and the office campus networks of the enterprise need to be completely reconstructed to IPv6. Once the IPv6 reconstruction has been done, the communication between the office campus networks and the internal application systems of the data center would have been switched to IPv6 single stack. Because the office campus networks need to access IPv4 internet content, we can reserve their internet addresses and deploy dual stack on these networks. After internet content is implemented based on IPv6 exclusively, the office campus networks will be switched to IPv6 single stack. After these three phases of IPv6 reconstruction have been completed, the enterprise networks would have been completely upgraded to IPv6. That's all for sharing. Thank you for watching.